time to start. And so as I said in the email, I haven't even started looking at the exams yet, and I'll get into those this weekend and endeavor to get them back on Monday just so that we don't get too far behind. The most important thing is if you haven't signed up for a paradox presentation, that you sign up for it by today, because you're going to need to get together with your partner if you have a partner. And there are a couple people who have signed up for topics who are still looking for a partner. So if you want to have a partner, take a look at the sign-up sheet, which is on the website. In the center column, sign up for one. Don't feel like you have to know how everything works when you sign up for it. Just if it feels like a compelling story, try your best to come up with your best explanation. You know, frequently when I first start thinking about things, I end up getting totally confused. I'm sure Dr. Katovid's the same way. That's natural. And if you're still confused come Monday, despite your best effort, we can schedule a meeting maybe in the late afternoon to kind of talk about your particular topic and maybe an approach or something. I will be more definite on the times that we will be doing these, but it should be Tuesday late afternoon. So that's after our Tuesday meeting in the tent for philosophy. We'll do some of them then. And again, it's supposed to be nominally a 10-minute presentation, so we could do 6 of them in an hour, maybe 5 of them with comments or something like that. So if we spend an hour and a half, and some people are doubling up in their groups, we can get through most of them, but whichever ones we don't get through, we will do Wednesday in the afternoon. That's the day we don't have a meeting, unless next week is different. We don't have a meeting of the philosophy class, so we'll meet with whoever's left over that afternoon and just see them. And if you feel like, don't feel like it has to be polished. This is not meant to be our final presentation of this, but I want you to concentrate on what is the argument you're making. I mean, first of all, make it appealing that the paradox actually seems paradoxical. That's part of the goal of the presentation. But then also having a clear explanation. And then if you have an idea of how to make the explanation, it's another level to think about how are we going to best illustrate that. As I said, I like things that are very visual. And so once you get the explanation more or less correct, then we can talk about visual ways you might explain it that will make it more intuitively appealing to people. Any other questions, concerns? There is ongoing now, there's chapter 13 and 14 homework. There's a sheet that has problems associated with both. So we're finishing chapter 13 at the beginning of today, and then we'll begin with chapter 14 today. I don't know that we'll get into chapter 15, but that follows right on the end of it. And that's it. It's really a progression from, think of the Lorentz transformation as being something that is a very useful tool. Perhaps it's not as intuitively exciting as the relativity of simultaneity or something like that, but it's an extremely useful tool that allows you to do a lot more stuff than just those 3 rules that we had before, and in fact, really easily. We'll see that in chapter 14. Chapter 14 addresses a long-standing question of, if one frame sees something going at a certain speed, that's not the speed of light. If that speed is the speed of light, then every other frame is going to see it as going at the speed of light. But if it's not going at the speed of light, how is a different frame? How fast is it going in that IRF? And then 15 gets to really interesting questions of, suppose, I don't know how, but something is going faster than the speed of light, all the mayhem that leads to as time goes on. Okay, so should have set this up before, but let me start the slideshow here. Let's see if my fancy pointer is working, and then we'll begin. We better turn out the light up here too. So many things to do at the beginning of class. Okay, so we were talking about the Lorentz transformation. What does it tell us? It tells us, well, so it's comparing coordinates of an event that happens between two inertial reference frames. So we have one labeled F and one labeled F prime, and the assumption is that F prime is moving relative to F in the plus X direction. Now that means that, of course, F is moving relative to F prime in the minus X direction, and so it's going to be almost the same transformation that goes between the two. But this is phrased in this way, where the relative motion as seen from F is in the positive X direction. If we know the coordinates of an event in F, we know what X, Y, and Z it appears at when that flash takes place, and we know the time according to its clocks. And again, the assumption is that these two frames at the time that we're going to require that their axes all coincide with each other at one instant in time, and that at that time, the clocks at the origins both read time 0, and that they're moving relative to each other in the X direction. So if we get those X, Y, Z, T coordinates, the question is, in this other frame, what are the X prime, Y prime, Z prime, T prime coordinates? And we're putting primes on them, or that little apostrophe thing, so that to remind us that it goes with this F prime frame. Okay, so all the coordinates there are labeled with primes. And we had to work really hard to get these formulae, but now we've got them and we can use them, and they actually are going to make our life quite a bit easier here, okay? What advantage is there to using the Lorentz transformation as compared to our other three effects, length, contraction, and so on? And the answer is, well, if things are just phrased in terms of events, it's much more natural to switch between frames and say, well, if somebody measured an event at this time, or maybe we're talking about two events, the example I gave is, suppose there's one event over here. I can't snap because my fingers are too dry, but an event here, and then a little bit later in our frame, an event over here. In somebody else's frame, what's the time difference between those events? It'll be different. What's the spatial difference between those events? It'll be different. And the Lorentz transformation tells us directly how to do that. And some practice with this is the second worksheet problem. Oh gosh, I didn't bring my worksheet solutions for this, but that's okay. The second problem, which is on the back side, I believe, of the worksheet that you already have. It's not the one I sent out this morning for those of you on Zoom, but it's the one that we sent out before Wednesday's class. And it concerns two events that happen at two different times. And of course, if we know the coordinates X, Y, Z, and T for event 1 and event 2 in one coordinate system, then we can compute what X prime, Y prime, Z prime, T prime for each of those coordinates are in the other coordinate system. And I believe you're asked, once you get the coordinates in the other system, what is the difference in time in the other one? And you're going to find out it's different than the difference in time in the first coordinate system. What's the difference in X in the second coordinate system? And it's different than the X in the first coordinate system. So dig out that sheet. Try to do worksheet problem number 2. I'm going to put, as usual, the Zoom folks in a breakout room. So make sure everybody who's in there try to participate and communicate with your fellow breakout room folks. Sorry, usually I bring one extra copy just for me to look at, but I didn't bring any today. So you might have to, well, maybe what I can do is if you can't find yours, I can bring it up on the screen here. Let's see. You might have to squint to see this, but here's the statement of problem 2. So we're given, you just need to sort of look carefully. It's giving you x, y, z. Well, y and z are both 0 in this case because the events occur on the x-axis. But it's giving you x and t for one event and the other event in one coordinate system. And we're told that there's a second coordinate system, or IRF, moving in the plus x direction with respect to it. And we want to find the x and t coordinates of the two events in the new coordinate system. So we have 4 computations to be done. What's x prime of the one event? What's t prime of the one event? What's x prime of the second event? What's t prime of the second event? And then we can calculate the time difference between the events. Anybody not sure how to begin? Remember, the Lorentz transformation equations are on the front of that worksheet. How's it going in here, guys? If there's a bit of calculation, you got to in your calculator. I mean, the first thing I would do is just calculate what gamma is, because you're using gamma 4 times. Rather than separately putting that square root in the denominator, just know that 1 over that square root is something you're going to multiply each time you use the Lorentz transformation equations. I get gamma is 2.294, so that's a useful fact. All right, I'm going to close the breakout rooms. Force them to come back, and then we'll look at the solutions. I think I'll just project my solutions up on the screen from the PDF. Okay, welcome back. I'm gonna share my screen again and discuss the solutions. Hopefully you at least got started on A, so you get, there's a lot of repetitive stuff going on here, but the idea is in this paragraph up here that I'm sorry, the class has the screen muted. In this second paragraph of the problem statement, you're given x and t coordinates for event 1. They're with a 1 subscript, and x and t coordinates for event 2. They're given 2 subscripts just to help keep them straight. And we're supposed to get the x and t coordinates in the primed IRF. That's why these have primes on them. Using the corresponding coordinates. So if I want x1 prime, I should put in an x1 and a t1 on the right-hand side of the Lorentz transformation equations. I was telling the class, gamma appears in all of these equations that we're going to be using. So it saves you quite a bit of time if you just compute gamma once and for all at the beginning. Since v is 0.9c, gamma ends up being, as I show over here, about 2.294. So I've calculated it once and for all. And then the Lorentz transformation equations are gamma times some other stuff that I can put in parentheses. So here's my 2.294. x1, you got to look up above, is 3 light years. And a light year is a c times 1 year. Minus v, in this case, v is the speed of the primed frame relative to the unprimed frame. That's 0.9c. And t1 was 1 year. So when I plug all that in, notice here I have a c times a year, and here I have a c times a year. Both of those combined together, you have light years. So when you put it all together, you get 4.82 light years. Is the x coordinate of event 1 in the primed frame. That's where they're going to measure it as appearing on their set of meter sticks that form that big lattice. Similarly, in the t prime 1, I've got to put a t1 and an x1 in the right-hand side. Slightly different formula, but no more difficult. We've got our gamma. T1 was 1 year, if you look at the details up above. And in this case, x1 was 3 light years. Again, I'm writing a light year as c times 1 year. And then I'm going to have a pair of c's in the numerator. Since we're dividing by c squared, I'll have a product of 2 c's in the denominator. I can cancel all those, and that just leaves years up here. Interestingly, we get a negative time there. That's kind of strange. We'll see we get a negative time for event 2 as well. So they occur both before t equals 0. And when we do the same thing for the x coordinate of event 2 in f prime, we get 7.34 light years. Any questions about just the mechanicals? I'm just turning the crank there, right? Not too much subtle thinking or, worrying about what I'm doing. I'm just plugging into the equations. Any questions about what I'm doing on that part? The upshot, or at least part of the takeaway, is to think about the answer to B, which is we can already see, I've underlined sort of a key relationship between E1 and E2 as seen in F. What I've underlined is they're separated in space by 2 light years and separated in time by 1 year. And in fact, event 2 occurs later than event 1. That's okay, so by 1 year. If we then take the corresponding difference in coordinates, in other words, if I do x2 prime minus x1 prime, what is the separation between them in the primed IRF. If x2 is bigger than x1, that means it occurs along the plus x direction relative to x1. And it does. It's 2.52 light years to the right along the plus x axis relative to x1. So that's the separation between them. Interestingly, when I calculate the difference in the times, t2 minus t1, I get a negative answer. And the question is, what's the interpretation of that? So if I look back over here at the subtraction we're doing, this is going to be negative if t1 is greater than t2 prime, right? If t1 prime is greater than t2 prime. The first event having a greater time value means that it occurs later, right? Greater time means it occurred at a later time in that frame. So that means E1 occurred at a later time, E2 occurred at an earlier time. So that minus sign is telling us that, in this case, the order of the events was flipped. Event 1 preceded event 2 in the F frame, but event 2 precedes event 1 in the F prime frame. And that might make you a little bit worried from the sense of causality. What if event 1 is a cause of event 2? And we'll find out later that the only time the order of these two things can be flipped in time is when they have no causal connection to each other. In other words, there's no way that event 1 could be some sort of partial cause of event 2 required for event 2 to happen. There's no way for that to happen because they're so far separated in space that the time separation doesn't allow for even a light signal to go between them, and that's the best we can do. We'll find out in the next couple of chapters. Questions on that worksheet? Most of what I'm forcing you to do here is just practicing knowing how to use these formulae. It's not that this is just mind-blowing what we're doing, but it's a very useful tool, and we're going to see it used again in the next chapter. Anything else? Okay, let me go back then to what we were doing here with the finishing up chapter 13. There's a particularly symmetric form of the Lorentz transformation, a way, if I look at these equations, it looks like, look what's happening in the numerator here for the x prime versus the t prime. It's kind of different. It's, there's still a subtraction happening, but it looks very different. The reason it comes down to that it's different is because, well, the units or dimensions of x and t are different. X is measured in meters, or it's a distance. T is measured in maybe seconds, or it's a time. And there's distances are generally very different than time, but I can make it look more symmetric if I change the units of this last equation to meters. And I can do that by just multiplying everything on both sides of this equation by c. So instead of expressing it in terms of t, I'm going to express it in terms of c times t. Remember, c is in meters per second, t is in seconds, so that gives units of meters. Then everything in all four equations will be referring to units of meters, and we'll see how that kind of simplifies things. So what I've done here is made sure that I replace every t with a c times a t. That can be accomplished in this fourth equation just by multiplying left and right side by c all the way through. We had a 1 over c squared, but when I multiply by c in the second term, I just get a 1 over c there. In the first equation, I'd like to replace this t with a c times t. And I can do that. I can put a c up in the numerator as long as I put one in the denominator too. So I just kind of forced it to work there. And now to really see the symmetry between these, the gamma factor is kind of distracting, so I'm going to write this in terms of gamma, but I'm also going to write v over c as beta. The Greek lowercase beta in relativity is oftentimes used to refer to denote the fraction of c that something is traveling at. It's another way to express the velocity. And that just kind of gets rid of some of the noise in the equation. So my v over c up here became a beta. Beta is just what fraction of c you're traveling at. Still multiplying c times t. And notice that exactly what's happening to x, how x prime depends not only on the x value in the other frame, but also its time coordinate. The relationship between those, telling me what the new x prime coordinate is exactly the same relationship of what happens to c times t prime. So there's really a strong symmetry between what's happening spatially and what's happening in the time direction. And we'll see that appearing when we talk about space-time diagrams in more detail later on. Merman talks about this in the book, doesn't he? Does he show a symmetric form of the Lorentz transformations? I can't remember if I added this on or if it's in Merman. I don't remember anybody commenting on it anyways. Okay, let's compare to what Newton would think. You know, maybe one way to make sense of this is to say, well, what would be the corresponding transformation between inertial reference frames that Newton would say? So I've phrased this as kind of a voting question. Oh, I know you don't have 6 fingers, but you can, if you want to vote for oh, actually you need 7. If you want to vote for G, you got to hold up 7 fingers here. You got to stare at this for a second because there's a lot of information on there. But imagine this is Newton contemplating this. There's nothing that he couldn't think about with this. He's just going to come to different conclusions than Einstein. Here's an event happening, and we've got our usual setup of the relationship between the two inertial reference frames. They overlap at time t equals 0 and t prime equals 0 on those, you know, the clocks at the origin, and then one's moving in the plus x direction with respect to the other one. How would Newton say if you measured x, y, z, and t relative to the blue coordinate system for this event? How would Newton or Galileo tell us how to compute what the coordinates would be in the red coordinate system, including the time? See if you can, you might have to look at this for a minute and really think about what is going on here. Okay, anybody have a strong opinion? Think they've figured out what Newton would say for this? This is sort of the Lorentz transformation, but we call it the Galilei transformation because Galileo and Newton would have had the sort of same intuitive opinion about it that we would have. Anybody see which way to go? Spencer's, yes, so Spencer is suggesting D or E. Anybody have an opinion about either one of those, a way to eliminate one of them? Beta is still V over C here, so it has the same meaning as before. Yeah, but I mean, so the first thing to realize is that anything that's got any reference to C in there seems very suspicious because Newton didn't think there was any, you know, as far as Newton was concerned, speed of light was infinite. And it certainly wasn't special. It just was, you know, if you could measure a finite speed of light, there was nothing special about it that would determine some random event's coordinates in going between two coordinate systems. So it seems like E is out. How about D? The suggestion there was for D. Anybody have a comment on that or agreement on it? Everett? I don't think that Newton thought that time would change. Yeah, Newton had this idea of absolute time, that whatever time, as long as we synchronized our watches at one time, and that's going to happen here, you know, we're same assumptions here, that as these pass by each other, both the corner clocks read 0. Well, of course, everybody's going to synchronize all their clocks, and there's no asynchronization. None of them run slower, and so we're always going to agree everywhere on the time that everything else happens after that, as long as we synchronize one pair of our clocks and all our other clocks are synchronized relative to each other. He's expecting that, we should be looking for something where t prime is equal to t. Everybody agrees on the time it happens once we synchronize our clocks with each other. Okay, so given that, do we have a better alternative, Everett? C, yeah, C combines what Spencer was looking at. The x coordinate is the other piece we haven't talked about. Of course, the y and the z coordinates still agree in a pretty easy way to see there, but the x coordinate is, if I imagine, at t equals 0, this red coordinate system was lined up with this one, then after a time t has elapsed, this distance the red one has moved is v times t, if it's moving at speed v relative to it. So this is v times t. And this whole distance here is what we're calling x, right? Because the blue coordinate system is saying, I measure this at x. So what would be the red coordinate system's corresponding x prime? Well, it's going to be the full x minus v times t. So that's called, the answer there is C, and that's called the Galilei transformation after Galileo, of course. And you can see it's quite a bit different, but remarkably, the Einstein one, the Lorentz transformation, has more symmetry. The Galilei one is sort of asymmetric compared to the Einstein one. The Einstein one says, hey, it's not just that something's happening to x, something's also happening to t in a very symmetric way, as long as we work in the speed of light in this particular way. So in some sense, it's, if you like symmetry, seems somewhat better, even though it's more complicated. Any more questions on the Lorentz transformation? For us, it's a tool, and we're going to use that tool right now to get one of our last big calculational results. And we'll find out it's not too bad to derive it. Okay, so this is entering into Merman's chapter 14, a simple way to go faster than the speed of light that does not work. If I were to label this in a normal textbook kind of way, I would just say this chapter is on what's called the velocity addition formula, which tells us how to do or not do something we assumed we knew how to do back in chapter 1, which is if you see something moving forward at 3 meters per second and I'm moving relative to you at 2 meters per second, then maybe I should see it moving forward at 1 meter per second. We're going to find out that that's not true in relativity. So our intuition that we used back in chapter 1 wasn't true. We normally add velocities in that particular way, but they're not going to add together. But still, people call it the velocity addition formula, even though the rule says you shouldn't just be adding them anymore. Okay? Here's the way that Merman suggests that we might think of progressively getting something to go faster than the speed of light. Start with a spaceship relative to Earth, moving at 0.9 c. Okay, that's perfectly allowed, or it doesn't seem like there's anything strange about it. We've been talking about things moving like that throughout the course. Have that spaceship shoot you in a pod ahead of the ship at 0.9 c relative to the ship. So if we imagine we're in that ship, we feel completely at rest. We blast off a little tiny pod with you in it at 0.9 c relative to it. And if we use our intuition from chapter 1, you and the pod will be traveling away from Earth at 1.8 c. That's what we would have assumed back in chapter 1. There's something that doesn't agree with relativity here because, that's also the same kind of reasoning that said, if I'm riding on a light beam and I shoot a light beam ahead of me, then it would be going at twice the speed of light relative to someone watching from the very beginning. And so it doesn't seem like it agrees with relativity, and it doesn't. So here's how we're going to phrase the problem, and I'm going to start out using a little bit different notation than Merman to try to make it a little bit clearer what we're talking about. I've got some IRF, which I'm going to call f prime here. So here's the x prime axis, here's the y prime axis, and something is moving, an object, so that object we'll call O, I'm just drawing it as a green block here, is moving with a speed v, and I call the subscript O f prime. That means the speed of O, the object O, with respect to the f prime coordinate system. So it's moving this fast relative to this set of axes. And you might be riding along with those axes, so you feel like those axes are completely still to you. Suppose somebody else comes along and says, well, wait a minute, I'm watching this whole set of events from a different IRF. This F prime axes are moving to the right relative to me. How are we going to denote that? We might call it the speed of the F prime relative to F. That's what the subscript there means. I just kind of made up that subscript. V F prime F means the speed of F prime with respect to F. So an object is moving with respect to F prime, but also F prime is moving with respect to F. And our goal is to figure out what is the speed of the object relative to F. That's the kind of thing we're talking about here, right? In the example we gave, this speed of this with respect to the original ship was 0.9 c, and the speed of the ship relative to Earth was 0.9 c. What's the speed of the pod and you relative to Earth? That's what we're trying to figure out. Hopefully not 1.8 c, or it seems like it shouldn't be that way. Okay, so the Galilean velocity addition formula, again, following Galileo, is, or what Newton would assert too, is the way we add velocities is to literally add them. In other words, if this object is moving at 3 meters per second with respect to this frame, and this frame is moving at 7 meters per second with respect to this frame, then this object should be moving at 10 meters per second with respect to the other frame. That's why it's called the velocity addition formula. The same reasoning, of course, applied to things going at 0.9 c would lead to the 1.8 c result. And so it seems like there's something that's not right with that, or not in agreement with relativity. And Merman warns us that, here when we're just, without thinking too much, asserting 3 meters per second, when we say something travels 3 meters, we have to say, as measured in what IRF? In 1 second time? Who's measuring that time? We're being a little bit too, flippant about doing this and not thinking carefully about what those numbers mean. Uh-oh. Lost control again. So this formula here, the Galilean velocity addition formula, is not the correct law for combining velocities, although it is going to be extremely, extremely close to correct as long as the speeds involved are not close to c. So there's nothing wrong with it. Galileo was perfectly right. He had no way to know what would happen when things were traveling close to c. Now in the book, in the reading that you did, you'll see that Merman has a different notation for this. He says the speed of the object that we're considering with respect to that first IRF, he denotes that by u. And the speed of the first IRF with respect to the second IRF, he denotes as v. So it's a little bit harder to remember what those mean. And then finally, the speed that we want to find of this object with respect to this first or second IRF is denoted by w. So the Galilean velocity addition formula would be w equals u plus v. That's what we want to improve upon here. And I think he begins, and so I'm just going to do it here the same way, starting by telling you what the answer is, and then we'll derive it in just a second. But just to think about the formula that we're going to derive in just a second, this is called the relativistic velocity addition formula. And of course, it's not a simple addition on this side. It's something more complicated than addition, so it's somewhat of a misnomer, but it's something analogous to adding. They don't add together. Maybe we should call it the velocity lack of addition formula. What it says is, well, notice that w equals u plus v is the same as it was before. The only thing is that we're dividing by something else in the denominator. And of course, when you divide by something, you make it smaller. So at least we have that hope that it might, if it started out at 1.8 c, it might get pulled down by that denominator. So compared to the Galilean velocity addition formula, we can see that, well, the denominator would be close to 1 when this factor, or this term, uv over c squared, is really small compared to 1. Well, if u is really small compared to c, we've got a c squared in the denominator. So if either u or v is really small compared to c, then that fraction that's being added to 1 in the denominator is going to be really small, and the denominator will be approximately 1. And the Galilean velocity addition formula will be a very good approximation. But if both u and v are close to c, that's like our 0.9c and 0.9c case, then it's going to differ significantly from it and make a big effect on it, okay? So if we use this with that example of the pod is moving relative to the ship at 0.9c, the ship is moving relative to Earth at 0.9c, that's telling us that u and v are both 0.9c. And we plug that into the formula, work it out, lo and behold, it gives us a number that's less than c. It's a little bit faster than either one of them, but it still doesn't go over c. It's 0.994 c is what people on Earth would see for that object. Okay, so that's just thinking about it. And now let's do the derivation. The derivation is surprisingly simple once we have gotten the Lorentz transformation. We're just going to use that and turn the crank here a little bit. So let's imagine in this picture, we're so used to things moving. Nothing's moving except something. Here's a train car. That's the blue rectangle. And we're going to shoot an object from one end of the train car to the other. And we're going to assume here, I didn't even label it on here, the length of the train car is just sitting at rest. It's not moving. Its length is d. And the time it takes this object to get to the other end, we're going to call t, capital T, okay? So if we denote the speed that it's moving at as w, then w, of course, will be the distance it moved divided by the time it took. And we're going to have to remember that later on because we're going to use that to get out a w out of something. To use the Lorentz transformation, we're going to define two interesting events. Event 1 is when this thing is shot from the left end. That's a publicly identifiable event. And event 2 is when it hits the other end of the train. Okay, and the coordinates, position and time coordinates, if I call the x-axis the direction along the train and place the x equals 0 position at the left end of the train car, then the first event occurs at x equals 0. At t equals 0, we're just going to, by definition, call that point, that event at t equals 0. And then the second event would occur at x equals d in time t. Super simple. And that's nice because we can plug that into the Lorentz transformation formula to figure out what the coordinates of these two events would be in this other frame that I'm drawing here. It's the f prime frame with x prime and y prime axes there, and it's moving at speed v relative to the train that's at rest. So it's going ahead of the train while this whole experiment is being run. And let's figure out what the coordinates of these events are in that frame. Again, subject to the idea that the two sets of axes overlapped at time t equals 0. That's when there are clocks at the origin, red t equals 0, and all that usual stuff. Okay? If we can find the distance that what we're heading towards is, if we can find the distance it moved, that's going to be x2 minus x1 in this frame, and the time it took, t2 minus t1 in this frame, that's going to, that distance divided by that time will be the speed that this thing is perceived as moving in this frame over here. So let's just throw it into the Lorentz transformation equations. Here they are, copied for your convenience over here. And let's calculate what x1 prime and t1 prime is. Whenever you have both x and something happens at the origin at time t equals 0, hey, that's really easy to plug in because the x and the t you're plugging in are both 0. That makes the numerator 0. And that makes the primed coordinate 0. So x prime is going to be 0. T prime is also 0 because both things in the numerator here are going to be 0 for that first event. Okay, so the primed coordinates for the first event are also x equals 0, t equals 0. What about for the second event? Well, there things are more interesting. I have to plug in just x equals d and little t equals capital T over here. And of course, we get something that's just plugging those into those two. So here are the x and t coordinates of the second event. And now I'm going to do what I said to do over here. U, by definition, is the speed of this thing in this frame is going to be the distance it moves divided by the time it took. Well, it started at 0, so the distance it moves is equal to this, and the time it took is equal to this because it started at time equals 0. So I just need to take the ratio of this x coordinate over this t coordinate, And when I divide them that way, something nice happens. That square root factor cancels out because it's in the numerator and the denominator. So the distance divided by time, which is u in this case, is just the one numerator over the other numerator. And that's not too bad. And by definition, that's u. So how are we thinking of u here? Well, remember, we have two frames. One is moving in the plus x direction with respect to the other one at v. That's what Merman calls v. And w is the speed of the thing with respect to this first coordinate system. U is the speed of it with respect to this other coordinate system that's moving. So that's the names we're using are really the ones that we intended to use here. So we found out that U, which is the distance it moves divided by the time it took, is equal to this. So I've got an equation here. What are we going to do with that equation? Well, I want to use the fact that W is equal to D over T by definition. Well, I don't see a D over T here, but what you can do is just solve this equation, the U equals this, solve it for D, and then divide by T, and you'll find that things simplify out. So I'm going to solve this for D. I'm not going to show the work here, but solve this equation I've created for D, and then divide both sides by T, and you'll get D over T, which is W, is U plus V over 1 plus UV over C squared, which was the formula we said we wanted to head towards. So that's the formula that tells us, again, as always, you don't need to know the derivation, but I like to go through the derivation. This one's not terrible. It's just practicing using the Lorentz transformation. It tells us that if an object is moving with respect to one frame at less than c, and that frame is moving with respect to another at less than c, then at least we have some hope that the object's speed with respect to the second frame is still going to be less than c. Before we show that, let's practice using this formula a little bit. So I'm going to pass out the worksheet. This is the one, for those of you on Zoom, that I attached to the email this morning. We're just going to start out, because we're not ready to do parts C and D, just 1A and B right now. Just phrased in terms of someone traveling between Earth and X, my favorite setup. And I'm going to send, as usual, the Zoom folks to a breakout room. Try to pull up your worksheet there. Hannah, can you hear me?
Yes, I can.
I'm not sure why you weren't assigned, but I'm going to put you in. Sorry about that. Something didn't happen automatically. Anybody need help getting started? just for reference, I think my answer to A was 0.988C. 0.988C.
Oh, that.
Okay, let's go through the first parts A and B together on the board, because part of this is just to make sure you understand what the symbols mean in the formula. So here we've got someone, X and Earth are at rest with respect to each other. They're in one IRF, and there's a certain X is a certain distance away relative to Earth, 10 light years. Earth sends Stella in a spaceship to planet X along a straight line at a speed of 0.8 c. Stella then, in A, shoots a probe out ahead of her at 0.9 c. What is the speed of the probe as measured by observers in the Earth X IRF? So in this case, we're trying to use this formula. I'll use Merman's notation. W equals U plus V over 1 plus UV over C squared. And the question is, first of all, what are U and V in here? Well, the U in Merman's notation is the speed of the object with respect to that first coordinate system, and the V is the speed of the first coordinate system with respect to the second coordinate system. So V is supposed to represent how fast Stella is moving in the plus X direction relative to Earth, and U is how fast the probe is moving with respect to Stella. Okay, so if you read carefully here, the things we're going to plug in are let's see. V is the speed of Stella with respect to Earth, and that is 0.8 c. And U is the speed of the probe with respect to Stella, that's 0.9 c. And so we just have to plug those in. And to calculate W, W is going to be the speed of the probe as measured in the Earth IRF. So let's calculate. W is equal to 0.8 c plus 0.9 c. I guess I switched the order of them in the numerator, but that doesn't matter. Plus, when I put U times V here, each one of them has a factor of c, which then cancels the c squared in the denominator. So this is going to end up being just 0.8 times 0.9. Because they each had a c next to them up here, and they canceled the c squared in the denominator. Throw it in your calculator, and I claim, this isn't my solution here, so where is my solution? I think it's 0.988 c. Yes. 0.988 C. Okay, that's A. Questions on that one? Either Zoom people or the class? Okay, then in B, we're going to do it again. This is the kind of thing Merman suggests doing. The probe itself shoots a bullet ahead of it at a speed of 0.85 C relative to the probe, IRF. What is the speed of the bullet in the Earth's IRF? So now we could think of what are our three different objects we're concerned with. We're concerned with the Earth IRF. We're concerned with the probe IRF. And we're concerned, our object here is that little bullet speeding ahead. Okay? And U, in Merman's notation, always represents the speed of this with respect to this frame. So in this particular problem, that U is 0.85 C. That's the speed of the bullet with respect to the probe. The V is always the speed of the one coordinate system with respect to the other, the one IRF with respect to the other. And in that case, that's the speed of the probe with respect to the Earth. That's what we found out in part A, right? So that's 0.988 C in this case. Okay, and so plugging in the same way, it's kind of the same calculation, but with different numbers in it. In the numerator, we have the sum of those two things, 0.85 plus 0.988, and they both have a C next to them, divided by 1 plus 0.85 times 0.988. And that number is, well, it's very close to C. It's obviously bigger than 0.988 C. I got, when I rounded to 3 places, 0.999 C. I don't remember what the place was after that, but it was a number less than 5, the next place, decimal place after that. Questions on that? Again, we're just turning the crank. You don't, other than deciding what the different values are, we don't have to have too much intuition about it. Okay. Let me briefly then go back to the screen share and go ahead by one slide, and that is addressing the question, well, sure, this maybe all works, but it was because everything was moving in the plus x direction with respect to everything else. What if they aren't moving that way? And I should say, we're not going to address the case where things are moving at odd angles with respect to each other. There's a way to decompose them and just use this multiple times, but it's just not worth doing in this course. We're going to imagine that always everything's moving along the x-axis. But what if the object, instead of moving in the plus x direction with respect to f prime, as I've got shown here in the picture, I've got the object moving in the plus x direction relative to f prime, just ignoring the red axes for the time. What if it moves in the minus x direction relative to f prime? Well, the same formula applies. We just make u negative. Call that a negative x velocity. What if f prime, instead of moving in the plus x direction relative to f, is moving in the minus x direction? Well, then v is negative. And what if, after calculating according to this formula, w ends up being negative? Then the conclusion is, relative to the red set of axes, this object is actually moving in the negative x direction rather than the positive x direction. Okay, so in all three cases, a minus sign just means that something is moving in the negative x direction, whether it's u, v, or w, relative to the thing that that symbol always indicates that it is. So now we're ready to do worksheet problems C and D, which involve a little bit more complication because not everything's lined up in the same way that they were earlier. And apparently, we're also ready to do problem 2, which is on the back side of the worksheet. So let's at least try to finish parts C and D, and then maybe we can do 2 together. just for comparison, on C, I get minus 0.833 C. If you're checking your work. Part C, minus 0.833 C. And D, I'm sorry, that's D. Looking at the wrong one. C is 0.357 C. Okay, it looks like everybody's back in the main room, so maybe I should turn on the light here for the benefit of those in the class. Hopefully that doesn't mess up our focus. C, while Stella is on the way to X, a probe is sent from Earth towards Stella's ship. Okay, so Stella, remember, was moving at 0.8 C with respect to Earth. And a probe is sent from Earth towards Stella's ship at 0.9 C. Okay. What is the speed of the probe as measured by observers in Stella's IRF? So in this case, that W that we want to find is the speed of the probe with respect to Stella. So Stella is kind of that backwardmost set of axes that we're going to compare everything to. And that W is the answer we want relative to Stella's frame. Okay. In this case, the Earth maybe is the intermediate frame. It's the one that we know the speed of the probe with respect to. So it's kind of like, you might say, we've got Stella's frame, and then we're comparing to that the Earth frame, and I think the thing was a probe here, right? Yeah, so then there's some probe. I don't know what a probe looks like, but some other thing that's sent ahead. That's the probe. So in this case, since I'm going to calculate what the speed of the probe is as seen by Stella, we want the speed of the probe with respect to Earth. And in this case, we've already been using the fact that the probe was moving in the plus X direction. So let's continue to call the direction that the probe and Stella were moving relative to Earth plus X. In that sense of using it, I would say the probe speed with respect to Earth deserves a plus sign. U is equal to, what is it? 0.9 C. V is the speed of Earth's frame with respect to Stella. Now Stella is moving in what we call the positive X direction. That means from Stella's point of view, Earth is moving in the negative x direction. And so that V deserves a minus sign. If we're going to call this one plus, this one's got to be minus. In other words, if we already decided the direction everything was being sent away from Earth, let's call that plus x, then Earth is moving in the minus x direction relative to Stella's plus x-axis. So this would be, got to read it again here. This is Stella with Earth with respect to Stella, and that was a factor of 0.8. So it looks like this should be a minus 0.8c, looking back up at the stuff at the top. And therefore, the W we want to find, that's the speed of the probe with respect to Stella, as seen by Stella. It will be, well, let's see. These two things get added together in the numerator. Doesn't really matter which way we do it. And then in the denominator, we put both those things multiplied together above a c squared. So that's a 0.9c, right, times a minus 0.8c. We keep the minus sign in there, even in the denominator, and then we're dividing by c squared, and that, of course, cancels out those factors of c. But we've got to put that minus sign in there. So we're doing 1 plus 0.9 times minus 0.8 in the denominator, which actually subtracts something off of 1 in the denominator instead of adding something on. And the answer I get when you put it in your calculator is 0.357c. And what that means is this probe is still moving in the plus x direction relative to Stella, as seen by Stella. It could have been that Stella was going so fast that the probe was getting farther and farther behind, even though they sent it in the direction towards Stella. If Stella were moving faster than the probe, as seen by Earth, it would get farther and farther behind, and then Stella would expect a negative velocity of the probe. But in this case, it's actually catching up to her, so relative to her, it's moving in the plus x direction. That's where we got this plus sign from there. Questions on that one? All right. D. While Stella is on the way to Earth, a bullet is fired from her ship directly back towards Earth at a speed of 0.98c. What is the speed of, oh, yeah, I think I changed this on yours. What's the speed of the bullet? Yes, as measured by observers in the Earth IRF. Okay, so again, what I want to know is the speed with respect to Earth, in this case, of the bullet. So let's change the picture here. In this case, you know, the way we have been drawing it, I want this thing that we're going to get the speed of with respect to be Earth. The intermediate one is Stella. She's firing a bullet, and I think she's firing it back in the direction towards Earth. Isn't that correct? So here's our bullet. And that means that, and that's the bullet's speed with respect to Stella, how it's fired there. So that means our u is going to be negative in this case. And what is the speed? 0.98c. So u will be minus 0.98c. V is the speed of Stella with respect to Earth. So that's still 0.8c, and she's moving in the plus x direction here. So we don't need that minus sign anymore. And then we calculate W the same way. And, well, it's not so interesting, the intermediate details here. But after you just plug those into the formula with the minus sign in both positions where U appears, you get minus 0.833c. That's the speed of the bullet as seen by people on Earth. Since it's negative, that means the people on Earth are going to see it moving in the negative x direction. That's the meaning of the minus sign there. Okay, so I know we haven't done the most general case where it's shot off at an angle, but at least if all the relative motion is along the plus or minus x direction, we've got the most general case here. All right, we've just got a couple more slides, so I'm going to go ahead and just finish up for chapter 14 to finish the story here, and then we'll start anew with chapter 15, which is very interesting. I mean, we're sort of going from technical results to really things that are philosophically interesting, logically interesting. This is an intermediate chapter. Okay, so what's the proof that successive boosts? We've only done this once, right? We said, okay, if I boost something ahead of something that's already moving at a fast speed, it's not greater than c. So, you know, we had an object relative to f prime, and maybe here's another frame, f double prime. That object, we could equally well think of it as another IRF, right? We've got one IRF moving with respect to another IRF, and that second IRF is moving with respect to a third IRF. The velocity addition formula is telling us that if, did I miss a slide here, or did I have it hidden? I'm missing a slide. Very strange. I changed some things right before class, but let me just see what happened here.
And we're also not seeing your screen. We're seeing.
Well, that's okay because something got messed up, but thanks for reminding me, and I will share it in just a second. There's a slide that I can't see, and it must be hidden. Yes, it is hidden. So let me get this one and unhide them. Not sure why they were hidden, but something went wrong there. Okay, so slideshow from current slide, and let's do share screen. There, should be able to see it now. Okay, so what's the proof that W can never be larger than C if neither U nor V is? We said, here's a generalized formula, but we still don't know that W might end up being bigger than C if we plug the right numbers into this formula here. The way to go about showing it, I think Merman has a complicated algebra way. I'm just going to do a visual way that's very quick. Here's our formula. I'm just going to divide both sides by C, and I'm going to express this denominator right here as U over C times V over C. And then let's divide, you know, so if W is 0.98 C, then W over C would just be 0.98. So W over C is the fraction of the speed of light of W, similarly for U and similarly for V. So we're going to call those fractions of the speed of light, capital W, capital U, capital V. I think that's Merman's notation, if I remember correctly. And then the only question is if U is between 0 and 1. In other words, U is less than or equal to the speed of light, and V is less than or equal to the speed of light. Can we show that W is between 0 and 1? That means that this W is less than or equal to the speed of light. And the easiest way I could think of doing that was to actually visualize this by programming it into a computer. So what I did was put it in a program called MATLAB and produce the following plot. You got to kind of digest this plot for a second, but that fraction of C of U is down here on the bottom. And notice it goes from 0 to 1. So we're going to say if it's a very small speed all the way up to close to C, that would be capital U being close to 1. That's plotted along here. And if V is all the way from 0 up to something very close to C, that would be capital V being close to 1. The color on this plot, so we just go whatever U is and whatever V is, we go to that corresponding coordinate here, we check out the color, and then we read the value of the color on this color scale over here. The important point is that as long as U is less than C, that means capital U is between 0 and 1, and V is anywhere between 0 and C, that means capital V is between 0 and 1. Notice the colors are always between what correspond to W being between 0 and 1. And so that means there's no way that you're ever going to see, at least in one step of boosting ahead, that, you know, if somebody shoots something off at any speed that's less than C, and they shoot something off that's at a speed less than C, then that with respect to the first frame is still going to be less than C. That's what that picture is supposed to be showing us, because it never went off of this color scale. It goes between 0 and 1. Well, what if you go to the next level? Okay, if I go to the next level and shoot something out of that, well, the same argument applies. Instead of imagining that this is an object being shot ahead, it's some other inertial reference frame, and we imagine shooting some object ahead of it. Maybe it could go over C with respect to this maybe Earth frame back here. But the idea is, if I forget about that middle, well, so what's true here is that the speed, if this frame speed with respect to this one is less than C, that's the first statement, and if the speed of this frame with respect to this frame is less than C, what we just showed with that plot is that the speed of this frame with respect to this frame would be less than C, okay? Once I've decided that, I can dispense with that red frame. So let's just kind of gray it out there. And then apply the same logic again. If this frame with respect to this frame is less than c, and we just concluded that that would be true, right? And this speed with respect to this one is less than c, then we can conclude that this one's speed with respect to this one is going to be less than c, and so on, and so on, and so on. No matter how many times you do it, you can just repeat the argument and show that the resulting speed with respect to the first frame is c. And therefore, no matter how many times you send something forward close to c and send something ahead of that at close to c, and so on and so on and so on, this process doesn't lead to a speed greater than c as seen by anybody's IRF. There's no way it can lead to that. And so that's Merman's proof that this is not a way that things can lead to speeds greater than c. That doesn't say that something couldn't just inherently travel faster than speed from the very beginning of time. But in any case, I'm going to stop there. This is just a summary of what we've done so far. We just introduced the relativistic velocity addition formula. That's this over there. And the important takeaway from this is that no matter how many times you boost something ahead and boost something ahead and boost something ahead, if all of those are less than c boost relative to the last frame, then relative to the very first frame or any other inertial reference frame, it's going to be seen as moving at speeds less than c. So we already knew that was true for light. Light always goes at c no matter how many times you shoot a beam from shooting a beam. But that's true for other things too. It doesn't exceed the speed of light.